Um, First of all, congratulations. You are the survivors. Actually, this assignment was not that easy as they were before, but at least I hope you found it fun enough. And your fine-tuned Trump large language model was able to produce something close to how Trump gives his speeches. So today we're gonna talk about LLM even deeper. Today we're gonna dive into code, and Michael will show in details how all these embeddings, how semantic search performs. So floor is yours, and I believe that this lecture is gonna be very interesting.
Nice, thank you very much. Hi everyone. Let me see if I can share the screen. That's usually the first thing to do, right? Can you see stuff?
Yes.
Yes, absolutely.
Can you hear stuff?
Absolutely.
Okay. So today's lecture is concerned with the code, the practical details, and the things you want to do when you actually work with the technologies that were discussed in the previous lecture. So today we talk about embeddings, tokenization, and semantic search. So semantic search is the way we tie all of this together. We work with transformers, the neural networks that were introduced in the previous lecture. We talk about embeddings, which are basically the outputs of a transformer. We talk about tokenization and other ways of um, analyzing or pre-processing our text. So last time we talked about theory. We saw that usually the way language models work is first we pre-process our text. In particular, we can, for example, tokenize it into tiny bits of language, into tokens. Next, we convert each token into an embedding somehow. Today, we will see how exactly this is done. And finally, well, I mean, finally, yeah, finally, we put this to work, put this into a neural network, into a transformer or sequence-to-sequence model, maybe some kind of recurrent neural network, doesn't really matter much. We put this in and get to work. It produces some kind of output, like a continuation of our text, or maybe classifies something or predicts whether the stock market will crash today or not, and so on and so forth. So all of this was just theory. Today we get our hands dirty. Today we dive into code, and we see how exactly we can use transformers and embeddings for fun and profit. In particular, we will have a look at tokenization, using various methods, starting from the very basics, like baby steps from str.split in Python, and work our way up all the way to tick token, which is the tokenizer used in ChatGPT. Next, we'll look at various ways of computing embeddings, starting again with not exactly baby model, but a very simple model or web2vec, and work our way up all the way to BERT, which is a model based on transformers. Finally, we are going to apply all of this to an actual task that can be useful in practice. We'll try to see how semantic search works. So let's begin by recalling how language modeling works in general. So we see here, let's me increase the font size and see if it crashes or not. Okay, so we begin with some kind of text. This can be anything. This can be like news article, some kind of paper, anything, any text you want to process. You start with this and you extract something relevant from it. You extract tokens because in general, computers work with bytes. So well, bytes and bits. So the most fundamental thing you can extract from text are bytes because everything in a computer, everything is represented as bytes. This video is bytes. This notebook here is bytes. My voice is bytes. Everything is stored as bytes. So in particular, when you're tokenizing your text, it's already tokenized. You don't need to do anything because it bytes all the way down. So you can use just the raw representation of the text. You can use just the bytes and somehow pass them into your pipeline. However, bytes don't make much sense, do they? In particular, you can use various languages where one letter is represented by multiple bytes. In English, it's easy. In English, one letter is 1 byte. This is called the ASCII encoding. But in other languages, like Hindi, you have one symbol. It can be represented by 4 bytes or more. So if you feed in just the bytes, the model will have to think hard to understand that, actually this sequence of 4 bytes isn't just some random garbage, it's a letter. Emojis are also represented by multiple bytes. So again, if you feed in just the raw bytes, the language model will have trouble understanding that this is actually an emoji and not just some garbage. This is why we use something more meaningful. We split our text into more meaningful parts, more meaningful embeddings or building blocks. So like language for humans is built from letters, morphemes, so words, and so on and so forth. For computers, we can do the same, actually. We can write complicated algorithms that extract letters, morphemes, and the words from our text. But another approach is to define our tokens as statistically useful chunks of text. This will be defined later, or well, actually, it has already been defined in the previous lecture. In particular, here it says useful chunks of text. Useful for what purpose, you might ask? One approach, the byte pair encoding, actually defines tokens as useful for compression. In particular, byte pair encoding isn't, again, new. It's not something that was created specifically for language modeling either. It was created for text compression. Algorithms like zip and gzip, stuff like that, deflate. These are compression algorithms, and byte pair encoding is a compression algorithm. It splits the text into tokens that help compress the text better. Naturally, while compressing the text, it creates a vocabulary of tokens. It creates the set of tokens that makes the text more compressible. It means you start with a text that has like 1,000 characters or 1,000 bytes and end up with a vocabulary of tokens and text that is now like 100 tokens. So you compress your text from 1,000 bytes into 100 tokens. I mean, this is way too much probably, but something like this, you get a compression ratio. So this is what I mean by statistically useful pieces of text. Now, you can put all of these tokens into something called a vocabulary, which is an ordered collection of unique tokens. You know, when you open a dictionary, you see definitions of various words. But in a dictionary, there are definitions, and in a vocabulary, there are no definitions. It's just a list. Doesn't need to be alphabetically ordered, doesn't need to be um, anything complicated. You just put your tokens into the vocabulary in some kind of order. So order is important because later on we'll see that we'll need to have a concept of token ID. So each token has an ID or an identifier, which is an index into this vocabulary. We see here token build, it has an ID of 1. Token block has an ID of 2, and so on and so forth. And token has an ID of 0 here. So we have tokens, the vocabulary, and token IDs, which are indices into the vocabulary. Basically, every token now is associated with an integer. Next, we want to feed this integer into the model. And last time, I said in a comment that you actually don't need to do this for a general computer because, again, computers store stuff as integers. Basically, everything in a computer is an integer. So you don't need embeddings to work with text in general. But neural networks always work with real numbers, numbers like pi, numbers like e and stuff like that, square root of 2, like 3.1. These aren't integers. So you somehow want to convert your token IDs, which are integers, into something that isn't an integer. This is where the concept of embedding comes into play. This is one of the papers that introduced embeddings. They called them word feature vectors. You know, from general machine learning, we always speak of representation. We always speak of features. We want to convert basically some real life object into a vector. We want to measure stuff about this object and put this into the neural network or your decision tree and stuff like that. For example, if you are dealing with humans, you can like measure their height, you can measure their weight, measure their age and stuff like that, and put all of these characteristics of a human into a vector, where the first dimension is going to be like the age, the second dimension is going to be the height and stuff like that. Same thing here, you want to describe each token or each word. You want to have a vector of 1,000 dimensions or something, where each dimension means something, and thus this entire vector can be passed on into the neural network. Moreover, such neural network is going to be differentiable because you know you usually train neural networks via gradient descent. It says gradient descent, so you want to compute gradients with respect to your parameters. So you want your parameters to be continuous because you can't differentiate with respect to an integer. But you can differentiate with respect to an embedding because embeddings are vectors in Rn. They contain real numbers. So this is the usual thing. You just build some kind of feature vector for each token. This is the same thing that is used in machine learning in general. So in particular, you can say, you know, this vector describes token number 19 using two features. The first feature is equal to 3.43. The second feature is negative. Okay. And then what you do, as usual in machine learning, you learn these features via maximum likelihood. You know, the usual thing from probability theory, from statistics, you fit stuff via maximum likelihood. You can do the same, you can fit embeddings via maximum likelihood. And to do this, you need some kind of objective. You need some kind of objective to optimize. For example, you can teach a model to predict the next token in the sequence. You can teach the model to fill in the blanks. Like, when you learn a foreign language, you have such exercises where they give you sentences with missing pieces, and you have to fill in the blanks. So this is the same thing. You can teach a neural network to fill in the blanks, and as a byproduct, you get embeddings, which are features that were specifically learned to be useful for this particular task. Like here, we said that a token is a statistically useful chunk of text, and in particular, byte pair encoding is useful for compression. Here, you have embeddings, which are useful for a particular task. You can't have just some kind of embedding because why? Usually, embeddings are specifically trained to be good at a particular task. For example, there are embeddings that are good at predicting the next token, filling in the blanks, comparing similarities between tokens, and so on and so forth. We know that embeddings are part of something called representation learning, which is a field of machine learning where the goal is to learn a representation that is useful for some kind of task like next token prediction. Again, you can have a look at the paper. It's one of the fundamental papers that introduced the concept of embeddings, predicting the next token, and so on and so forth. Here we have an example vocabulary that I created myself. It's basically just a list, nothing fancy. We want to see what kind of tokens we have, what kinds of token IDs we have. So for example, the token has the ID of 0, token word has the ID of 6, the token of has the ID of what's that, 10, and so on and so forth. Obviously, in a real world application, you have thousands upon thousands of tokens, of unique tokens in your vocabulary. Now let's have a look at the first baby approach to tokenization, which is literally calling str.split. Here's the code. You have your text. This is the text. You call that split, and it splits on white space in this example. So you have the output above. You see that we got our tokens. Each token is a word, approximately. So we have embeddings, which is a word, are part of representation learning and stuff like that. So each token is basically a word. But since we split on white space, we have some weird stuff like a token that begins with an opening parenthesis. We have weird tokens like this, which ends with a closing parenthesis. So this needs some tweaks. We don't want to split on white space usually because there's punctuation. When there's punctuation, there's trouble because you don't really understand whether something is punctuation or should be treated as a single word. For example, E dot G dot probably shouldn't be split by the dot, right? Because it means this like combination of symbols means the same thing, means for example, and same thing here. At all, you don't exactly want to split this up because it means the same thing. It means and others, stuff like that. So this is the baby's first tokenization approach, splitting by white space. Again, as we see, it's extremely easy. It's one line of code, very simple to implement, very simple to understand. As a human, you see that it usually gives you individual words, so you can interpret this somehow. However, in other languages, perhaps they don't split their text on words. Maybe there are languages like that, so it doesn't may not work for all the languages out there. What's more, here it says that forms of the same word are now different and completely unrelated tokens. You can say embeddings or embedding in singular. They will be different tokens, completely unrelated. Maybe we don't want this. And as well, punctuation becomes part of words, which isn't exactly desirable. So we may want to somehow split by punctuation. As an example, we can download some kind of Wikipedia page, like for Python, their programming language. I'll share the code. You will see how this is done. So we download the text of the Wikipedia page, and we literally split this on white space. Here are the first couple of tokens. It says Python is a high-level general-purpose programming language. Its design philosophy, something, something. And again, we see that there's this comma here. Doesn't need to be here because high-level is the word, but high-level comma is not a word. We don't really want to see this comma as part of the token. We can like count stuff. We can count the number of tokens. This is how many tokens we have. In total, we can count how many times each token appears on the page, which can be useful for some kind of approaches to computing embeddings. As you know, computing embeddings can be done in multiple ways. Using neural networks is not the only approach. You can build co-occurrence matrices, for example, extract embeddings from that. And for this to work, we will need to be able to count the number of occurrences of various tokens. So this is how we can use literally split Python's built-in function to create baby's first token. Now let's move on to tokenization using something called word pieces. Word pieces, this is something we saw before. This is what the byte-pair encoding does. It constructs in a particular way parts of the text that are deemed statistically significant, statistically important, stuff like this. Here we'll see how byte-pair encoding can be used in practice. For this, we have the library called tokenizers. It's provided by Hugging Face for free. You can download it right now. It provides tools for training tokenizers. Here we use BPE, which is the usual byte-pair encoding. We have some kind of process for training the tokenizer. And as a pre-processing step, we can do multiple things. So in particular, here we will convert our text to lowercase. Here we tell the tokenizer that before analyzing the text, we want to convert it to lowercase. Why? Because maybe capital letters don't add much information in your particular application. Maybe they do. Maybe you don't want this feature to be enabled. Then, again another pre-tokenization step, we split by white space, which is exactly what we did above with the str.split. In particular, it turns out that if you split your text by white space and apply BPE to each such substring, you will get more useful tokens. So we do this here. We lowercase the text, split it by white space, and apply BPE to individual substrings like this here. Finally, we create a trainer as our text that we extracted from Wikipedia and train the tokenizer. So far, so good. Another interesting thing is that we can have unknown tokens. This happens when the training corpus isn't that good, it's too small. So when we try to apply the tokenizer to a new unseen text, it may struggle to extract, may struggle to find tokens to tokenize. So if this happens, we'll have an unknown token. Okay. And now the idea is that our vocabulary no longer consists of whole words because we build our words from statistically extracted pieces, statistically meaningful pieces, which are useful for compression in this case. So this is basically an application of machine learning. So we here learn our tokenizer from data. You see here, we define the model, we get the data, and then we train the tokenizer from the data. So if your data set is too small, if it's not representative, and so on and so forth, your tokenizer will be bad. It won't be able to compress the text well enough. It won't be able to represent the data well enough. So it may seem like BPE is just some kind of algorithm, but no, we can treat it as a kind of machine learning algorithm as well. So the main idea here is that your tokenizer, resulting tokenizer, will depend on your training data. Let's see this in action. We have the tokenizer, so we train it here, train it on just the text about Python, their programming language, nothing serious here. Trained it, and let's have a look at the vocabulary. I mean, part of the vocabulary, because the vocabulary is huge. We have 3,500 tokens in the vocabulary that were automatically used, automatically learned using BPE. So we have the following tokens. For example, support. Well, we see here that BPE is able to sometimes learn entire words. Somehow, for some reason, for BPE, it was well important to select an entire word and use it as a token. Cool. But then we have stuff like conform, which is not necessarily an entire word. You can have words, derived words like conformity and stuff like that. You have a part of a word, like early. I mean, the entire word is probably early year, early yes, something like this, but we have a part of the word. And so on and so forth. We have like NE, which was extracted for some reason. We can have a look at other slices of the vocabulary. We have theory, which is a part of a word like introductory, and so on. So the idea here is that we trained our tokenizer to extract parts of words, to extract building blocks of words. So now our tokens aren't just entire words, they are subwords, they are word pieces. We have tons of them, 3,500, and we can have a look at their IDs. For example, there's a token Python. Obviously, this makes sense because the text is about Python, so Python is its own token. ID number 88. We don't have a token prog. You know, I thought that the text is about programming languages, right? But we don't have this token. We have programming as its own token. So on and so forth. You can apply this to tokenize unseen text. So we trained, the idea here is that we trained the tokenizer on a particular text. We took the Wikipedia page about Python, the programming language, and trained our tokenizer solely on this particular text. We can apply the trained tokenizer to encode unseen text. In particular, here's a random text I came up with. Python is a programming language and Julia is a programming language used for scientific computation. This is a text that does not appear in the training set. Yet, somehow, we can tokenize it. We see that Julia is its own token, probably because Julia is mentioned on on Python's Wikipedia page, is a general purpose programming language used for scientific computation. So we managed to tokenize a piece of text that does not appear in the original dataset. This is basically what tokenizers are for. You train them on a particular dataset and apply them to other unseen datasets. This is what machine learning is about. Okay, but this text about Julia is still about programming, right? So it's the same application domain. Let's apply our tokenizer to punchline, to jokes and humor. Here's a random piece of text from the page linked here. It says a linguistic interpretation of the mechanics of the punchline response is posited by Victor Ruskin in his script-based semantic theory of humor. And we can just guess that Python, the entry for Python doesn't talk about humor at all. Let's see how our tokenizer forms here. Oh no, we see, for example, the word linguistic here is tokenized into 4 tokens. So it's really inefficient. We have one word, right? One word, one meaning, but now we have 4 tokens. So if we think about our future machine learning approach, our neural network or something like this, that will be applied to these tokens. This neural network will need to learn that linguistic, this particular stream of tokens means linguistic, actually. It's not just random garbage. So our tokenizer, it did the job. It tokenized the unseen text, but didn't do it quite well, right? Another example is mechan x. It's a single word, right? So again, the neural network will have to spend the extra compute to understand that mechan x is a single word, stuff like this. Again, here, Victor Raskin. Again and again, so we see here that we have tons of characters, right? Tons of characters. And we compressed these characters into just 37 tokens. Again, we did compression. BPE and the tokenizers in general, they compress text from tons of characters, tons of bytes, into, as we see here, just 37 tokens. But we are struggling here because we trained our tokenizer on the entry for Python, the programming language. So a text about programming, but here we applied it to a text about humor. The tokenizer is struggling to generalize. As we see here, it split linguistic into 4 tokens. But it still works. The tokenizer has never seen this text. It only ever knew about Python. It knows about Python, nothing else. But somehow it's able to tokenize the text about humor. This is great. This means that we can apply this tokenizer to process basically anything that contains English language, the Latin alphabet. Well, in particular, we can notice an interesting observation. We see that interpret is a separate token. Wow, what the, okay. So in particular, we see that interpret is its own token. We can find it here, right? Interpretation. And we may wonder why interpret is its own token. I mean, if it's own token, then it must be important for the token. It's important because Python is an interpreted programming language. So interpret appears many times in the Wikipedia article. So interpret is occurs often enough for it to be its own token with its own ID. Again, each token has an ID, which is an integer. Let's move on to how an actual language model works. Let's see how ChatGPT approaches the problem of tokenization. We see that OpenAI provides a library called TikToken that implements the literal tokenizer used in ChatGPT. So this isn't some kind of toy, nothing like this. This is actually the tokenizer that's used literally in ChatGPT. In particular, we see GPT-4o uses the tokenizer returned by this function. We can apply it immediately. We don't need to train anything. It's pre-trained by OpenAI. We'll talk about pre-training later. So the main idea here is that this tokenizer is ready to use. Moreover, it's the literal tokenizer used in ChatGPT. So we can trust OpenAI for it to be good. Let's have a look. We load the encoding for GPT-4o and query the number of tokens in the vocabulary. We see that GPT-4o has 20,019 tokens. This is how actual ChatGPT will see your text. In order to communicate with you, in order to understand what you write, in order to answer, it will use 200,019 tokens. That's it. That's the size of its vocabulary. Let's see it in action. We can tokenize the string hello world, and it does really well. It says hello, comma, world, and an exclamation mark. So that's great. It doesn't use any rules. It doesn't know what punctuation is, probably. Well, I mean, maybe OpenAI hard-coded punctuation into the tokenizer, actually. So the idea here is that it's pre-trained. We don't need it and don't need to train anything. We successfully tokenize hello world. We can tokenize everything else. We can have a look at our text about humor. The same text, our tokenizer tokenized into 37 tokens. Here, we see the ID of tokens produced by ChatGPT. We see we have 27 tokens in total. We used to have 37 tokens, now we have 27 tokens. We may think that this tokenizer by TikToken is better at compressing our text compared to what we trained manually using just the Wikipedia entry for Python that program. So this is the literal tokenizer used by actual ChatGPT. You can go to ChatGPT, talk to it. It will talk to you using this vocabulary. It will split your text into this vocabulary. It will respond using this vocabulary. In the same vein, you can go to DeepSeek. It's open source, open weight. You can have a look at the tokenizer used by DeepSeek. You can look at tokenizers used in Qwen and the other language models. Okay, we covered the first part of the lecture. We talked about tokens, which is a way of representing language for machine learning. Are there any questions about tokenization? No questions about tokenization. Great. Let's move on to learning embeddings for our tokens. First, let's deal with the word embedding, because it has its own meaning. So to embed means to make something an integral part of something else, or to insert something into a computer document. And embedded, which is an adjective, means that something is set firmly into a mass or material. And here, why the things are called embeddings, maybe because we are embedding discrete tokens into some kind of real vector space. We have tokens, token IDs, which are integers, and we would like to insert somehow them into the vector space, convert each integer into a vector. So the main idea, the main purpose of embeddings, the main characteristic of embeddings is that words with similar meaning have similar vectors. Words with similar meaning have similar embeddings. Tokens with similar meaning have similar embeddings. We can ask what we mean by similar meaning. We don't really know. We are like humans, so we kind of inherently know what similar meaning is. Only us humans know what we mean by similar meaning. And the computer doesn't. That's the entire point. The computer sees everything, all text, as just a bunch of bytes. It has no concept of meaning, no concept of similarity, nothing like that. But when we convert words or tokens into embeddings, into vectors, we immediately gain a notion of similarity. We gain a notion of vector similarity. So while the computer doesn't know what similar meaning is, it knows perfectly well what similar vectors are. Uh, Vectors are similar if they are close together. For the notion of closeness to make sense, we need to define some kind of distance between vectors. So, for example, we all know the Euclidean distance, the Manhattan distance. There are tons of distances we can define. We define a distance in our vector space, use just the usual Euclidean distance from linear algebra. So we can say, okay, two vectors are similar if they are, this close together. But this begs the question, why 0.1, maybe 100, 1,000, something like this? Why this particular number? Why this cutoff? We can improve this by using cosine similarity. So cosine similarity is closely related to the Euclidean distance. Again, a notion from linear algebra. Cosine similarity is related to the cosine of the angle between two vectors in the vector space. So this is literally this, the cosine of the angle between two vectors x and y in our vector space. And again, I say vectors x and y, but here we are talking about embedding. Embeddings are just vectors, nothing fancy. So we can do math on them. We can do linear algebra on them. This is the definition of cosine similarity. It looks exactly like the Pearson correlation coefficient. It's basically the same thing. It ranges from -1 to +1, where negative values mean that the two vectors point in opposite direction, and positive values mean that the two vectors point in the same direction. And so now we can quantify similarity. If the cosine similarity between two vectors is positive, we say they are similar. If it is negative, then they are antonyms, basically. If it's exactly 0, they are orthogonal, they have no relation to each other. Now let's have a look at how to learn embeddings. One of the first models to deal with embedding, to learn embeddings from data, called word2vec. It was discussed in the previous lecture. So here the main idea is that we look at rolling windows over our text. Looks like this. we have a piece of text which says, and when the cat saw some fish, it said something. We have talking cat here. So our goal is to look at a window around the token cat. So the token cat is called the middle token, and it's situated in the middle of the window. The window is here in blue. When the cat saw some, it's our window that we look at. Look at the window and see what kind of tokens surround the token cat. Again, the middle token in red. We see here that the token when, well, uh, the token when is in the window around the token cat. One, yes, the two tokens co-occur in this window. A token they, right here, occurs around the token cat in the window, one, and so on and so forth. The token some occurs in the same window as well. So our neural network or some kind of machine learning model will have to predict, given the two token IDs, it will have to predict one or zero. We will have to classify this pair. Do these two tokens occur in the same window or not? Here we have our sliding window. It will move, and the next middle word will be saw. It will be colored red, and we'll again analyze what words co-occur with the word saw. We have so-called positive examples. So one means yes, the two tokens co-occur in the window. So if we just run this procedure, we'll see that everything is a one, right? We slide our window across the text and do this operation for each middle word. And like obviously everything will be a one because we only look at the window. We don't look outside the window. So the model will be really dumb. It will predict one for everything. It will predict one for any combination of tokens you throw at it. So this is not what we need. So we need to manually supply negative examples. We need to manually supply combinations of words of tokens that do not occur in the window. This is done randomly, so this is not part of the sliding window procedure. In particular, we see that cat and dog do not co-occur, cat and tree do not co-occur, and so on and so forth. So we build positive examples of tokens that do co-occur within the window and negative examples, pairs of tokens that do not co-occur. And then you literally train a classifier like a neural network to distinguish between co-occurring and not co-occurring tokens. You train this by modifying embeddings of each token. So as we know from the previous lecture, each token is associated to its own embedding, its own vector. So for example, the token cat has its own vector, the token saw has its own vector, and so on and so forth. So initially, these vectors are random. We'll literally generate them using random sampling because the initial configuration, well, it is believed that the initial configuration doesn't really matter. We generated them randomly. And then we run some kind of neural network to classify these pairs and update our embeddings using gradient descent as usual. This is what is done in GenSim. It provides a word-to-vec, which is an implementation of the word-to-vec training algorithm. For this to work, we need to split our text about Python into sentences or like pieces of text. So I randomly split this on exclamation points and new lines and stuff like this. So this is a design decision. You decide how to split your text. As an example, we got this as a first sentence. Python is a high-level general-purpose programming language, stuff like this. So these are tokens generated by TikToken, by OpenAI's library. We built the sentences. We have, wow, we have 555 sentences in our text about Python, the programming language. And then we simply say, okay, let's train this word vec with these sentences with the sliding window of length 5. Here we have the same length actually. 1, 2, 3, 4, 5. 5 words in each window. So this means in particular that we are guaranteed to have a middle word. We just postulate that our each embedding will have 10 dimensions, and we run this for 100 epochs. Okay, this trains in like 2 seconds. It's really simple because we have only 500 sentences. It's really, really, really low. But it's just an example. In practice, you get like you download the entire Wikipedia, which is like gigabytes and gigabytes of text, and you train your words vec on the entire Wikipedia. We can have a look at the tokens generated by the tokenizer. We see that Python is number 3, A is number 4, and so on and so forth. This is our vocabulary. We see it here in action. And then we have word vector. You see here WV, it means word vector. So you can, it works like a Python dictionary. You can index into it and ask, what is the word vector for the token Python? You know, for some reason here we have a space. This is how the tokenizer works. Here we see these are our 10 numbers. This is our learned vector representation of the token space Python. So that's it. We see like now an embedding isn't something abstract. We see it here, this stuff, these numbers. This is an embedding for the token Python. And similarly, we can query any other token. We can say, oh, well, tell us more about the token language. This is the embedding for the token language. And so on and so forth. We can query more properties of the embeddings. We can have a look at what words, what tokens, what embeddings are most similar to the given token. So we call most similar to the token Python, and we would like to get 10 tokens that are most similar to Python. We get this. We see that the token developers is the most similar, with cosine similarity equal to this. The token 2 is the second, with cosine similarity equal to this, and so on and so forth. So the main idea here is that for each pair of tokens, you can now compute cosine similarity, because under the hood, tokens are computed to vectors, and with vectors, we can do linear algebra and compute the cosine similarity. So the closer it is to 1, positive 1, the more similar the two tokens are. Of course, here we use a small corpus, a small amount of text to train our model. We use just the Wikipedia entry for Python, the programming language. So that's not a lot of text. This means that these particular embeddings are probably terrible because they were trained on very few data. This is why we see the term big data thrown around. This is exactly because more data usually equals to better models, better representations, better embeddings in our case, where better means that embeddings better represent similarities between words. The usual example is that we can take the embedding for the token king, extract, subtract manliness from this embedding, and add womanness. And we, as humans, expect that when you take king, subtract manliness and add womanness, you will get something close to queen, right? Because queen is the woman equivalent of king. This, if you train your word-to-vec model long enough, if you train it on a corpus long enough, you will get this exact relation in the vector space. You'll be able to compute embeddings for the words king, man, and woman, do math on these embeddings, and literally subtract and add them. You will see that the resulting embedding that you get by taking king, subtracting man, and adding woman, the resulting embedding will be close to the embedding for the token queen. It won't be exact, but it will be close. You'll be able to plot the vector space. Well, I mean, not the entire vector space, but a projection of the vector space. And you'll be able to see with your own eyes that this combination of vectors literally lies close to the embedding for the word queen. So indeed, somehow the model learned that this semantic relation between human words can be translated into linear algebra and vectors. So this is again the main idea of vectors, is that they try to embed, let's say, the meanings of words into linear algebra and vector spaces. Now we'll move on to a more serious models. We'll look at BERT, which is a family of models known as bidirectional encoders for transformers. Again, the main discussion about transformers was in the previous lecture. Here we only look at the very basics.
Sorry for interrupting you. We have a question in our chat box. Is it okay that Python is similar to Python?
Is it okay that Python
is similar to Python? Yeah.
I mean, it's not okay. It's our goal. It's our very purpose. Our very purpose is to train a tokenizer, or I mean, a model, which makes similar words similar, actually. So yes, Python with a leading space actually should be almost equal in the vector space to the token for Python, because it's Python. It's the same thing. Python with a leading space isn't much different from Python without the leading space. So it's not only okay, it's our very goal. We want similar words to produce similar embedding. And if we get that, then we're golden. So that was that. Now we return back to BERT. BERT is a kind of neural network which is based on transformers, which were discussed in the previous lecture. Here we only look at the basics. The training objective for BERT is to fill in the blanks. We put in some kind of sentence like, so long and thanks for all the fish. This is our original correct sentence. We randomly mask some tokens from it. Like here, we say so mask and mask for all apricot fish. So here we can see that we mask some tokens and replace other tokens by random garbage. And the task of the transformer is to predict that, actually we don't have this mask in the actual text, we have the token long. And here, instead of mask, we have the token thanks. And here, instead of this garbage apricot, we should have the token there. And so on and so forth. We run, GPUs, compute clusters for weeks and months, and train the embeddings. Here we see embeddings right here. These these things represent embedding. These traffic lights represent embedding. We train them as part of the overall model. And as a result, we get a model that will output embeddings when we put in our text. So this is exactly what I said just now, right? So again, here, the task itself, filling in the blanks, is just not useful, right? We don't usually do this as humans, right? How often do you fill in the blanks? Not all the time. So the task itself is not really useful, but the resulting embeddings are, and we will see this here. Again, we saw that this is just some kind of transformer, some kind of massive model, and we don't usually have the computing power to train it. Thankfully, there are pre-trained models. Above, we saw that we can easily train words of back, and we can train our tokenizers when our training set is small. We just took the Wikipedia entry for Python. It's really small. We trained our models in less than a second, was really easy, and the models were really good. And the training models on really serious big data sets is really costly. You need GPUs, you need massive, massive computing power. And you can click on these links and see that indeed actual data sets used for training language models contain terabytes upon terabytes of text scraped from the internet. There's a massive project that walks the web basically and visits all the websites and downloads all the text that's on the website. So they scrape 10 to the power 9 of these URLs basically every month or something like this. So you can click the link, you can see what the website looks like, and you can actually download these data sets. You can download this text for free right now if you have decent internet. If you have like about 10 terabytes of storage, you can download this text for free easily. You can train your neural networks, you can train your embeddings, and so on and so forth. But generally, these data sets are even larger than this, and only big corporations and the research centers can actually train useful models. Some of them release these pre-trained models for us to use. So here we see that there is this amazing company called Hugging Face, or the Hugging Face emoji. It provides storage and distribution for pre-trained language models. You can click the link and it will take you to the stuff. Oh man, you will be able to click the link in your files. You can click the link and see that actually, yes, the Hugging Face repository stores pre-trained models that you can download like this. There's a Python library. Python is great because there's a library for everything. You can parse the web. You can, process audio. You can process text, and you can also download transformer models from Hugging Face. So this is the library by Hugging Face. We import auto tokenizer and auto modern. So this might be this is funny because usually you train tokenizers, you have to train the tokenizer, you have to design the tokenizer, you have to design your model, you have to train, you have to waste computing power, you have to find bugs, stuff like this. Here we just say, hey, auto model, and it will automatically search for the model on Hugging Face. It will automatically download the model from Hugging Face. It will set everything up for you to use. In this example, we use BERT, which is a kind of BERT we discussed above, trained by Google. So imagine this, Google trained this model using massive computing power, using their GPUs, using their resources, using the employees. They wrote code, they bought the GPUs, stuff like that, and they just release it for free. You can use it right now. So we need a tokenizer, we need an embedder or a BERT model, and we can basically use this exactly like TikToken. We say tokenizer BERT and pass the string so long and thanks for all the fish. We show here the input IDs. We see that these are again the token IDs that we know and love. Actually, this function returns more data than just the token IDs, and we would like to put everything into the call to the model. So we use this star star syntax to pass everything the function returns into the model. Indeed, we can just call embed a BERT, and that's it. It will return embeddings that look like this. Look like this. So under the hood, somewhere in the code, there is a massive neural network chugging along, processing our input, burning our CPUs and GPUs. And as a result, we get this massive pile of numbers. Here, a massive amount of randomly looking numbers. From this, we can extract embeddings for each token. So we get this matrix here. This matrix contains embeddings for our token. Each row is an embedding. So this row selected here is the embedding for the first token. This row is embedding for the second token. This row is a vector, a feature vector, an embedding for the last token. So great. Now we know how to extract embeddings from transformer model. Here we have 10 tokens, and each token has 700 something features. Again, this is the number of automatically learned features for each token. Okay, this is exactly what we want. We got the features, and we can immediately put this into our neural network. Say you want to tell whether some text is positive or negative, whether it reflects positive or negative emotion, whether it means that the GDP will grow or fall, something like this. You can just put text into your neural network, but you can put in embedding. You get the embeddings, put them into the model, it chugs along, wastes your GPU, and you get the result. Another thing that we have that the model provides is this massive pile of numbers. This is a single embedding, not this one, this one. This is the embedding for the entire text. So here, up above, the text is so long and thanks for fish. These are individual token embeddings. We have 10 embeddings, 10 tokens. And based on this, we can average them. We can average 10 embeddings, compute the usual average, and get, as a result, something called Fuller output. This is the embedding for our entire string of text. So now you can say the text so long and thanks for all the fish corresponds to the embedding, the massive 700 numbers shown here. This opens up massive possibilities that will be shown later. You can further simplify the API. You can further simplify your task as a programmer by using a different library. You know, we used like 4 or 5 libraries now. Here's another one called Sentence Transformer. It's a library meant for extracting just the sentence embedding. So the job is to extract embeddings for the full text. We have a question in the chat. What's the purpose of averaging embeddings? The purpose of averaging embeddings is to get one embedding per text. Again, up above here, right here, we have one embedding per token. You tokenize the text into 10 tokens, and each token has a corresponding embedding. So your text, so long and thanks for all the fish, it's represented by this massive matrix. Okay, but we may want to represent the same text by just a single vector. So remember that when we discussed embeddings in general, we said that embeddings represent tokens, right? This is the basic idea. Embeddings represent tokens. But in the same vein, you can have embeddings that represents entire text. This is a powerful idea because now we combine embeddings for multiple tokens to create a single embedding that has the meaning of the entire text. So the purpose of pooling or averaging embeddings is to get a vector that represents the meaning of the entire text, not just a single token. This is exactly what we'll do here. We have sentence transformers, the library. We import the sentence transformer class. And again, Hugging Face helps us. We get another model. You can use different models to compute embeddings. We use this model because it's really small. We use this to compute embeddings for a bunch of sentences. Again, here we have several sentences. Python is a high-level, general-purpose programming language. That's the first sentence. Its design philosophy emphasizes code readability with the use of significant indentation. That's the second sentence. Python is dynamically type-checked and garbage collected. That's the second sentence, and so on and so forth. So our goal now is going to be to convert each sentence into an embedding. So earlier, we saw how to convert tokens into embeddings. Here we convert sentences or pieces of text into embeddings. So that's a different kind of task. Again, we get our sentences. What do we do next? We just literally say sentence transformer encode sentences, and as a result, we get this matrix. So the first row contains the embedding for the first sentence, the second row has the embedding for the second sentence, and so on and so forth. So now we moved up in the hierarchy. We used to have a single embedding per token. Now we still have that, but we can also average these embeddings to obtain a single embedding per text. In our case, per sentence, per chapter, and so on and so forth. So our intermediate results are like this. Tokenization converts text into discrete pieces that we can work with. Tokenization converts language into something computers can understand. In particular, every single piece of text that you see is already tokenized because it's represented as bytes. Bytes are a kind of token. You can have other kinds of tokens like characters or entire symbols like this gold medal. It's not represented by a single byte, it's actually represented by multiple bytes. But as a human, you understand that this is a single character. We also saw that we can use words and subwords as tokens. Then we saw how to represent these tokens as vectors. So we used embeddings that are defined as feature vectors associated with tokens. In usual science, let's say in usual science, you define embeddings yourself, or I mean, you define features yourself. You come up to a person and ask them questions, ask their age, gender, height, stuff like this. But here in machine learning, we can learn features automatically. This is the main purpose of machine learning, of neural networks in particular. Learn features automatically. This is exactly what we do here with embeddings. Embeddings are learned for a particular task, like predicting the next token or filling in the blanks. And as a result, you get random looking vectors that represent your token. For example, if we look here, what in the world does this number mean? Nobody knows, and we don't need to know. The main idea is that they help us solve our underlying task. Let's see an example, semantic search. In semantic search, the goal is to find documents that are close to our query. We need to find documents that answer our query. We need to find documents that are somehow similar to the query. We basically talked about this already. We can do this using embeddings as follows. First, we compute document embedding. As we saw above, we can simply average token embeddings to produce an embedding for the entire text. Say you have some kind of paper or a piece of the text in the paper, and you can compute a vector that represents the meaning of this part of the text. You can compute an embedding of like a news abstract and stuff like this. You compute document embeddings first, and now each document has a corresponding vector which is situated somewhere in our many-dimensional vector space. This is the image in 3D, 3 dimensions, and the red dots are our documents. So the main idea, again, is as usual, is that we associate with each document a vector. Since it's a vector, we can do math on it. Since we have a transformer model, we can build an embedding, a feature vector for the query. Suppose you have some query, you want to know whether you know who is currently the president of the United States or something. You get this literal text, who is the president, converts it into an embedding using the transformer like we saw above. It's here, the blue cross. It's the embedding for the query. And you literally look at all the other surrounding vectors. Your goal is to see which vectors are closest to the embedding of the query. This is vector search. This is semantic search. This is an instance of semantic search that has become popular lately. So, yep, we get our documents, embed them into the vector space. So we get the query, embed it into the vector space, and we need to see what vectors are closest to the search vector. We can use this, we can implement this using k nearest neighbors. I'm assuming you are somewhat familiar with the basics of machine learning, and thus you know that k nearest neighbors is one of the most basic, most simple classification and regression algorithms. So we literally take our query vector and see which vectors are closest to it, which vectors are its neighbors. A simple approach to this problem is just brute force search, which means that you loop over your entire database. You take all the documents, all the vectors, loop over all of them, and manually select the vectors that are the closest to the query vector. This is implemented here in this function. You can read it later. Here we have an example vector database. You probably heard this term that has become quite hype lately. This Python dictionary is a vector database. You know, these are vectors. These are documents. Hello, hi, dog, hound, and wolf are our documents. And we see, as humans, we see that the second dimension here represents like greetings. See, hello and hi, very high in greeting, and dog, hound, and wolf are low in greeting, right? So this is a contrived example because I know what I want to show. So here, let's say we are looking for greeting. Our query vector is 0, 1. We're looking for something that is high in greeting. Indeed, if we literally enumerate all our database, we get the correct answer. We'll see that hi and hello have very high cosine similarity with the query vector. This is obviously a example. Here we have a way more serious one. We use an actual vector database that stores our vectors and performs search. So the main goal of databases in general is to store stuff efficiently and to search for stuff efficiently. Like SQL or SQL, it provides a language for search, and the underlying database stores your data and implements efficient algorithms for search. When you say select stuff from some database, inner join and something, you express your desires in a language, but under the hood, there are complicated algorithms and data structures that actually perform the search. Same thing here in vector databases. The main idea is that you use k nearest neighbors to efficiently search for the vectors that are closest to the query vector. As we saw above, we can't use our brute force approach at all because you can have hundreds and thousands and millions of documents. You can't possibly enumerate all of them. So for this, there are algorithms that implement approximate k nearest neighbors. We don't talk about them here. Here are some links. You can look up approximate k nearest neighbor search. Let's see a quick example of this in practice. We import Chroma, which is one particular vector database. There are others listed above. We create a client that does not send telemetry to Chroma developers. We create a collection. So in Chroma, a collection is basically a table of data. And then we insert some data into the table. We say, okay, we have the following documents, and each document has a corresponding ID. In this example, the documents are news articles taken from the corresponding URL from CNN. So here we have like some news about celebrities. We notice how we simply call upsert, which basically means insert, and that's it. We don't have any embeddings, we don't have any tokens. Everything is hidden under the hood. Now that this is done, we can perform search with a single function call. We say collection, query, and pass the text. In particular, here we are interested in the following question: who is now a mother? Let's see what the database says. It found the following document here. And the first document reads, "This summer we welcomed our sweet baby girl." Great, so someone has become a parent. So this is a hit. The second document is 11 has become a mom. Okay, so again, this is a hit. We found what we are looking for using embeddings and transformers and tokenization under the hood somewhere in the library. And the final third text, because I asked for 3 texts, it talks about some Kirsten Dunst, probably. There's no information whether she's now a mother, just some kind of unrelated text. So we see here the key idea is that none of the documents actually contain the word mother. If you, I chose this query specifically because these texts, some of these texts, talk about motherhood, talk about babies and parenthood and moms, but they don't contain the word mother literally. Yet somehow, through, let's say, the magic of machine learning and embedding, we found what we were looking for. We found documents that are close to mother, and these results are actually correct. This is a manifestation of the main property of embeddings. Embeddings for words that have similar meaning are similar in terms of linear algebra. So when I say it query, the database performed vector search over vectors, and through this purely mathematical operation, we managed to find documents that are semantically similar to the query. This is the main idea, the main purpose, the main thing about embedding. Now let's see an easier example. We just search for something about Tarantino, just like Tarantino, because I know for a fact that the text talks about Tarantino. Indeed, it's the first hit as a Hollywood filmmaker Quentin Tarantino that revealed something. So here we see that we can search for words that do indeed appear in the text just as well. And again, the last sentence here, last document, doesn't really have much to do with Tarantino, right? So like pure nonsense, but the first text is 100% hit. Okay, this brings us to the end of today's lecture. Today, we saw that you can build your own search engine using embeddings, transformers, and tokenization. First, you tokenize your text, compute embeddings using a transformer, and use vector search to actually perform the task. We note here that this is not actually a chatbot. It doesn't talk back, doesn't respond, it doesn't generate its own text, can't write its own answer. It just finds the nearest neighbors in the vector space. Obviously, here we use English, and transformers and this entire technology comes from basically the United States, where we speak English. Of course, many models work best with English. So if you want to use this for other languages that are different from English, that use different scripts, for example, you won't be able to use these exact models. Or perhaps you will be able to use them, but you may get terrible results. Because as our first model was trained on the Wikipedia entry for Python, these models are trained for English text usually. So you will have to search on Hugging Face, actually, you will have to search for models which support your target language. Indeed, you can do this at home because thanks to Google and other companies and other people, we have pre-trained models which are available for free on Hugging Face. Finally, this whole technology can be used for fun and profit. The next lecture is going to be about retrieval augmented generation, which further applies this idea to search, to language models. And this is something that many companies are now trying to do because, they're trying to capitalize on the current hype. So if you want to dive into this, then you certainly have to learn more about transformers, embeddings, and language modeling. Thank you for your attention.
Thank you very much for your profound and very interesting lecture. So, in the meanwhile, we will send the home assignments, I think, in a couple of hours, by the end of this day for sure. And thank you very much for your attention.
Thank you.